when we now work in 3 dimensions and we have two three-dimensional vectors. They're both non-zero and they're not parallel, right? Neither of them is a multiple of the other. So these two vectors are not parallel. So, okay, that's all we have. You can see, first let's just get oriented with them. So I'm going to move these labels so that you can kind of see them. You can see which way they're pointing, right? Kind of. So as it now turns around, I'm going to let this rotate until the X and Y axis are kind of pointing towards us a little bit more. And then I'm going to stop the picture. So you can kind of see that they're pointing, those two vectors are pointing away from us, right? Just so you can get a sense of what's going on. Now let's identify these vectors with their points. So don't worry about the arrows. Think of the vector v as this point and the vector u as this point. The reason we're going to do that is because I don't want to have to draw an arrow for every single vector on this diagram. I want to just draw them as points because it's going to make a lot cleaner of a picture. Okay, let's start including some linear combinations of u and v. So what's that? That looks like, probably based on the parallelogram rule, that looks like what you would get if you just added u and v together. So that's a linear combination of u and v, right? 1 times u plus 1 times v. That's a linear combination of u and v. Here's another one. This looks like what you would get is if you took 1 times u and then you did v and then v again. So 1 times u plus 2 times v. That's what the linear combination is that we just plotted. Here's another one. This looks like it's just u and then u again. Well, there's no v, but that's okay. That just means the coefficient will be 0. So this point here is really 2 times u plus 0 times v. And then this one would be 2 times v plus 0 times u. Here we've got 1 times v, but then we're going in the opposite direction of u to get here. So this is like 1 times v plus negative 1 times u. That's a linear combination. And then now I'm just going to fast forward through a whole bunch of these. And if you're interested, pause the video at any time and you can try to figure out what any of these are. I'll give you a hint. They're all chosen with whole number integer coefficients just to make things simpler. But let's just try to see what shape is emerging here. I'm going to stop here and just leave it at that. Now let's kind of rotate this slowly and see if you can kind of pick out a shape that's formed or that's starting to emerge. And in fact, I'm even going to get rid of that gray XY plane just because I think it gets in the way a little bit, and this is maybe going a bit fast. You can see that there's some straightness here, right? There's some sort of straightness. It's like there's a level surface that's kind of being formed. And if we took all the points in between, like remember all these points are just linear combinations of u and v with integer coefficients, but if we took decimal coefficients and took some more precise numbers, we would generate a whole bunch of points in between, and we would start to see a plane emerge. Now where is the plane? Here we go. No, that's not what I wanted. Why does it keep doing these lines? I don't want a line here. Here, I'll just add it manually. There. So that's what you're going to see. As you plotted more and more of these points, you'd start to see this plane emerge. And I'll just rotate it around a little bit so you can see that really every one of those points, they really do lie exactly on the plane. This plane really does contain all the linear combinations of u and v. And not only that, it contains exactly all the linear combinations of u and v. So if you have any vector that's not a linear combination of u and v, it will not be part of this plane. It'll be, if you plotted it as a point, it would be some distance away from the plane. So this is just a more of a interactive justification that if you take the span of two non-zero, non-parallel vectors in three-dimensional space, it's going to generate a plane. And just like the line example, it's a plane that contains the origin. Note that the origin was one of those linear combinations. The origin, you can always write the origin as a linear combination of any collection of vectors. Just take 0 to be all your coefficients. In this case, the origin would be 0 times u plus 0 times v.